Hello everyone, welcome to part 5 on Intro to Spinors. So, in this video, we are going to cover Weyl spinors and chirality. Let's recap the past 5 videos. So, in our first video, we talked about what a spinor was in quantum mechanics. A spinor is just some superposition of the spin up state and the spin down states. This was an Intro to Spinors 1. And we talked about how spin up corresponds to a particle going up under some magnet, and spin down corresponds to some particle moving down once it enters the magnet. And that particle, of course, has spin, right? In part 2, we learned that spinors transform with SU2 rotation matrices, in that they're kind of like the square root of vectors. So it can take some polyvector, or matrix vector, as I like to call them, and write it as some tensor product of two spinors. So each spinor can be said to be like the square root of that polyvector. In the third video, that was the one titled the space-time algebra. We actually derived the Dirac equation, and we argued as to why the Dirac equation should actually have 4 components. Now, in that video, I wasn't quite sure why the Dirac equation is a spinor, but I actually know now. In the next video, we are going to talk about not why the Dirac equation is a spinor, or why the Dirac bispinor is a spinor. In the next video, I will be talking about why exactly the Dirac bispinor is a spinor. Here's a hint. It transforms with one SU2 rotation matrix. Okay, and also, wait a second. Oh yes, in the next video, we talked about the block sphere. This is Intro to Spinors 3. And the block sphere is like some way to visualize spinors, right? And yeah, just some way to visualize the rotation of spinors. And then after that, Intro to Spinors 4, we talked about the algebraic theory of spin. And so spin is just a quantum number that determines the possible values for the angular momentum of a quantum number. And the total spin is the eigenvalue of the spin operator matrix. So basically you have some state Sm, and say S is like 1, M is -1, 0, 1, M is constrained by S, where M is the angular momentum quantum number. And we learned that S equals 1/2, M equals 1/2 corresponds to spin up, S equals 1/2, M equals -1/2 corresponds to spin down. Now in this video, this beautiful video, we will talk about the Weyl spinors. So first, you're going to talk about chirality, and then I think we're going to talk about spinor fields, then the Weyl spinors and the Dirac bispinor, then Weyl spinors rotation and boost, and then finally the Weyl spinor metric. So let's actually begin. Okay, so what is chirality? What is chirality? Well, chirality it's a pretty cool concept in physics, and it's related to helicity. In chirality, it's kind of like a concept like spin and charge. Now, spin is like some intrinsic property of a particle. That's what's usually said. Like, it doesn't matter what frame of reference you're in, the spin of a particle is always measured to be the same thing. This is the same thing with chirality. Now, if you guess you may be familiar with a concept called helicity, which kind of deals with like the orientation of motion and the spin. Chirality is kind of like helicity, except that helicity is dependent on your frame of reference. However, chirality is invariant under change frames of reference. And to be a bit more specific on what chirality means, we say particles with particles with spin are left chiral if they interact with the weak force. So they undergo weak interactions. That's what left chiral means. Now, right chiral right chiral. Particles with spin are said to be right chiral if they don't interact with the weak force. All right, that's just what it means. So, yeah, and basically, I think actually it should be if they undergo weak interactions. I think that's a bit more explicit. If they do undergo weak interactions, they're left chiral. If they don't undergo weak interactions, then they are then they're said to be right chiral. And nature kind of picks out particles that are left chiral and that are right chiral, but they're still the same particle. For example, electrons, some can be left chiral, some can be right chiral. So there's kind of like a left-handedness and right-handedness in nature. And oops. Nothing went wrong, but I could have worded this better. Left chiral particles, they also have something called isospin. And right chiral particles, they don't have isospin. So probably worded it better. Left chiral particles have isospin, and then right chiral particles don't have isospin. And isospin is what allows a particle to undergo weak interactions, and lack of isospin does not allow a particle to undergo weak interactions. So just like how charge makes a particle be able to interact with the electromagnetic field, the isospin of a particle allows it to interact with the weak field. And if it's left chiral, has isospin, which allows it to have weak interactions. Right chiral, no isospin, no weak interaction. That's what chirality means. Okay. And what's next on our list? Okay, now we need to talk about spinor fields. Okay, so what is a spinor field? Well, spinor field is how can I describe this? A spinor field, it's like a function that takes each space-time point and assigns it or maps it to a spinor. And if we should know what spinors are by now. Since this is spinors 5, right? So we should already know what spinors are. A spinor field is just a function that takes a space-time point, gives you a spinor. For example, here's an example of some spinor field. Say it had like, I don't know, like 1 0 x 1 0 x, okay, where x is just some space-time point, okay, and x, I should probably use better notation here. Let's use the notation, I don't know, like x squiggly line on top. So this means a space-time point where x squiggly line is just the row vector, x0, x1, x2, x3. And this is an example of a spinor field. Let's just call the spinor field psi. Here's just some example. Since we can have the space-time point 1 0, I don't know, 2 1, just making up something random. And the spinor field will be, or the spinor field at that point would be 1 0, or the spinor it's called the spinor, what's it called again? The spinor strength at that point would be 1 0 multiplied by actually could define it a bit better. Yeah, let's change this field. So it's psi 1 0, but instead yes, okay, now I know. Sorry, let's ignore that. I want to give a better example. So psi, let's just say we have some field. It's 1 0 times x mu, where this x vector is just some space-time point, x0, x1, x2, and x3. And this is just the dot product of that. So say you have some space-time point 1, 0, 2, 1, make it something random. This means that x mu would just be 1 minus 0 minus 4 minus 1, which is just 1 minus 4 is minus 3, minus 1 is minus 4, and our spinner is now minus, it's now 1, 0 times minus 4, which is just minus 4, 0, and that's our spinner. That's the field strength of our spinner at the space-time point x naught, x1, x2, x3, which is, spinner point at x equals 1, 0, 2, 1. So that's the strength of our field at that point. So we see how this this field is like a function. It just takes some space-time point, assigns it a spinner. That's what a spinner field is. Alright, so what's next on our list? After that, we need to talk about what Weyl spinors are. That's the main topic of this video, alongside with chirality. So, if you guys can remember from my space-time algebra video, we actually said that the Dirac bispinor is a 4-component spinner with psi naught, psi naught, psi 1, psi 2, psi 3. Okay, so this is the Dirac bispinor. If you guys are unfamiliar with that concept, I recommend watching my space-time algebra video. Pretty good video. So this is the Dirac bispinor. Now, what are the Weyl spinors? Well, the Weyl spinors. Let me just write down the Dirac equation, since it would make sense to write it down right now. So this spinor satisfies this equation. We're actually going to derive this equation in the next video on quantum field theory. But here's the Dirac bispinor, solves this equation, and the Weyl spinors are like kind of the parts of the Dirac bispinor. So these two parts are said to be Weyl. I'm sure it's Weyl or Weyl spinors. So basically, the Dirac bispinor can be separated into like two smaller columns stacked upon each other, and in the smaller parts they're just called Weyl spinors. That's the definition for a Weyl spinor is. And sometimes we call this this upper chunk, we call this well, not call this, we use the symbol chi for this upper part, and for this lower part we use the symbol, well, people usually use the symbol zeta. Personally, I hate that Greek letter, so I'm gonna use epsilon to denote this lower side. So now psi can be written as chi and then epsilon. And sometimes people do some relabeling, and instead of say, okay, chi is just chi 1, chi 2, and then epsilon is just epsilon 1, epsilon 2, like making the Dirac bispinor now just chi 1, chi 2, epsilon, epsilon 2. So that's also a valid way of notation. So yeah, chi and epsilon, these are said to be Weyl spinors. Now this is why I kind of talk about chirality in the beginning of this video, because it turns out that the upper Weyl spinor is actually left chiral. Did I talk about what left chiral? Yeah, I did. So it's actually left chiral. And the lower spinor is actually right chiral. So like the spinor, the upper part, it's going to be left chiral spinor. Lower part, right chiral. So here's like a more concrete example of this. So say I have some Dirac bispinor that's 1, 0, 0, 0. Okay, this is of course just going to be chi 1, chi 2, epsilon, epsilon 2. So here chi 1 is 1, and all the other inputs are 0. So this means that the field, you see that the field is in the left chiral state, as you could say. It's in left Chiral space. It's a left Chiral spinor, and it's spin up, right? Because we have 1, 0. That's just the spin up vector. However, if our bispinor was instead, like, for example, 0, 0, 1, 0, then our bispinor would be in the right chiral state, but it's going to be spin up. So to put it in more explicit fashion, chi is chi 1, chi 2. Sorry, in more explicit fashion, chi 1, 0 corresponds to a left chiral spin up field, and then 0, chi 2 is a left chiral spin down field. And then you guys probably guessed it, epsilon 1, 0 is the right chiral. I'm not going to write down the entire list, but this is the right chiral spin up field. Here is the right chiral spin down field. All right. So you might be asking, well, why is the top part left chiral, bottom part right chiral? I don't know the answer to that question. Maybe if I do, though, I'll write down in the comments. Okay, so we talked about what the Weyl spinors are. Now let's get into the juicy parts. How do these spinors transform? How do they deviate from 4 vectors? You might be surprised to learn that these are actually 4 vectors. Because like quantum mechanics can never be simple, right? These look like vectors. Their components are kind of like four vectors. Well, they don't transform at 4 vectors, but, like, 4 components, right? They are defined on space-time, but they're not actually 4 vectors, right? Okay, so first of all, let's actually talk about what a 4 vector is. So, like, a kind of a recurring concept. I'm just gonna talk like a while, right? I write this down. A recurring concept in like pretty much physics as a whole is that I can't actually talk while I write down, sorry. But let me just talk. A recurring concept in physics is that we kind of define things in terms of transformations. For example, you might have heard the meme, a tensor is something that transforms like a tensor. And I say, well, that's a horrible definition. But turns out that's actually a really, really good definition. Because the tensor is actually defined on how the mathematical object transforms. And tensors like don't transform. So tensor transforms like a tensor being that doesn't transform at all, right? So we define mathematical objects in terms of its transformation. So if you show me some mathematical object and its invariance under transformations, and like the components transform with some number of Jacobian and inverse Jacobian matrices, then I have a tensor. That's how we define it. Similarly, with 4 vectors, we define it in terms of how they transform, and same thing with the Weyl spinors. They're defined as how they transform. Well, we define them as like the upper, like bottom part of the Dirac bispinor, but they transform in a certain way, making them a spinor. So let's actually talk about what those transformations are. So now we can write things down. So let's talk about how 4 vectors transform under a rotation about the x-axis. Okay. Also, I'm not going to give a crash course on 4 vectors. That's pretty much a prerequisite to this video. If you guys don't know what 4 vectors are, well then, I haven't made a relativity playlist. But you can check out my tensor calculus playlist. I talk about vectors like in the beginning, and I talk about component transformations, and basically 4 vectors. The component transform with that backwards matrix, but that backwards matrix is now the Lorentz matrix. And you can just look up what the Lorentz matrix is. It's pretty like analogous to each other. That's where I really like tensor calculus. It pressure very directly special relativity and general relativity. But no more let's actually continue. So 4 vectors transform. So let's talk about how 4 vectors transform under rotations around the x-axis. This is how they transform. Basically, I have x naught. I also want to emphasize something. I was being a bit lazy with my words. 4 vectors don't actually transform under rotations. This may surprise some of you guys. What do you mean 4 vectors don't transform? Well, the 4 vectors are invariant, right? Since vectors are tangents, tangents are invariant. The 4 vectors don't transform at all. The 4 vector components, though, do transform. Remember, a tensor is incomplete without a basis. Take a tensor components, attach second basis onto it, take the tensor product between those two things, you get a tensor that's invariant. So simply, this is how 4 vector components transform under a rotation around the x-axis. So you have x naught, x1, x2. And by the way, this is just, you can just look up this table online, and these are like tildes now because they're transformed components. We have 1 0 0 0 0 1 0 0 0 0 cosine minus sine, and 0 0 sine cosine. Now, since this is a pretty big thing to write down, I'm just using the shorthand that sine is defined as sine of theta, and cosine is defined as cosine of theta. And this is a rotation about the x-axis, and this is a 4 vector, well, the components for it. So how do 4 vectors transform under, well, the components, how do 4 vector components transform, to the whole thing, under a Lorentz boost? Well, and this boost is going to be a boost on the z direction, because that's the things that we're going to care about in this video. So boost along the z direction, we have x tilde naught, x tilde 1, x tilde 2, x tilde 3. The matrix is going to be gamma 0 0 minus gamma beta 0 0 minus gamma beta 1 0 0 0 0 0 1 0, and then 0 0 gamma, and then oops, I forgot to multiply this by x naught, x1, x2, x3. Should be multiplied by that, the OG of 4 vector components. And I have x naught, x1, x2, x3. So alright, and this is how they transform under a Lorentz boost. All right. Okay, so now let's talk about how the spinors, the Weyl spinors transform, to show you how they're different from 4 vectors. They transform in a very different way. Because remember, these Weyl spinors. Well, actually, it would be more fair to talk about the Dirac bispinor, since it's also 4 components. But that will be the next video. But basically, the Weyl spinors, there are 2 components, right? So it makes sense that the rotation matrix and all matrices that it acts on should be a 2 by 2 by 2 matrix to make the dimensions work, right? We can't like multiply matrices with different dimensions. I guess we can define it though, but like for our purposes, it's undefined. So let's talk about how the chi. So for our purposes, let's just talk about how chi. Actually no, let's cover both cases. Okay, let's cover both cases. So chi. Let's talk about how chi rotates about the x-axis. We have chi 1, chi 2, these components, and our rotation matrix on about the x-axis is going to be cosine of theta over 2 times I sine of theta over 2, I sine of theta over 2, and cosine of theta over 2. So symmetrical, right? And then of course times, oops, these should be tildes, times the original left Chirality Weyl spinor. Okay, so what about how chi changes, or about chi changes under a boost along the z direction, or the axis? That's going to be chi 1 tilde, chi 2 tilde. You guys might be asking, how do we find these things? We can actually derive how it would transform, but just take these as a postulate for now. I don't want this video to be too long. It's already like 24 minutes right now. So you have chi 1 tilde, chi 2 tilde, going to be e to the e phi over 2 0. Yes, I think we might be deriving these in some future video. Let me know if you guys want to see me derive this. This is going to be chi1, chi2. So this is how it transforms under a boost along the z-axis. So what about the right Chirality spinner? Well, the right Weyl spinner is how it rotates. Sorry, it's epsilon. How does this rotate about the x-axis? Well, it's actually going to be the exact same thing. It's going to be the exact same matrix with the left Weyl spinner. It's going to be cosine theta over 2, I sine theta over 2, I sine theta over 2, cosine of theta over 2 times epsilon 1, epsilon 2. And yeah, it's the exact same matrix we use. However, the boost about the z direction, it's a bit of a different story. So you have epsilon 1, so 2 tilde. Boost is going to be e to the minus v over 2, 0, 0, e to v over 2, epsilon 1, epsilon 2. So the boost is it's similar, but except that we kind of take these components and we just swap them together to get the correct matrix for the right Chirality Weyl spinner. So yeah, that's how they. So you can see how they're different. Of these, the corresponding matrices are different. And in fact, you guys can show that do this yourself. I'll be doing this in the next video. We can kind of show how a 360-degree rotation of the 4 vector is a. Well, I guess it would make sense, right? Well, for a 360-degree of a 4 vector will actually be a 180-degree of a rotation of a Dirac bispinner, which is a cool thing. That's actually how we defined spinners in my SG rotation video. So that's how you'll see why the Dirac bispinner is a spinner. Well, we're gonna do that in the next video. All right. So almost last thing. What's next? We have to talk about so talking about spinner rotations and boost, Chirality, Weyl spinners, spinner field. Last thing is the Weyl spinner metric. Okay, so let's talk about the Weyl spinner metric. All right, so the metric. Yeah, so let's first talk about the Minkowski metric. Now the Minkowski metric. I'm not going to derive this. You can find the derivation in any standard SR, not even standard, just any SR textbook. This is the we use the most minus sign convention in this video because that is the objective correct convention. And this is the Minkowski metric. It's the orthonormal metric. And the really cool thing about this is that if you study tensor calculus, which you probably should if you're watching this, the metric tensor components will actually change if you change your basis. However, for our case, Minkowski spacetime, it's actually a really cool spacetime in the sense that if you change your basis, or a valid basis through Lorentz transformation that does not include accelerated frames, the metric is actually going to be. The metric components are actually going to be the same. The metric components are invariant under these specific transformations, under orthonormal basis vectors. So that's a really cool property. So when we actually talk about transformations, you're going to see me write the same exact Minkowski metric, and that's actually why. Okay, well this isn't really metric. This is a metric tensor. Right, given some basis, but it's independent among bases that we care about. So hey, no more rambling. Let's just continue. Okay, so this is the metric tensor, and if you want to take the dot product of some 4 vector with itself, we're gonna have vi, vj, and ij. I'm using a bit of a different notation from the standard book to kind of match my earlier playlist on tensor calculus where I use this notation. So this is the dot product of the two vectors with itself, and we define the dot product as this because this is actually invariant. This quantity can be invariant under all our transformations. You can prove this yourself. We're gonna prove that for the left Chirality spinner. Okay, so similarly, there is a metric tensor for the dot product of two spinners. All right. So if I take two spinners, how should I write this notation? If I take a spinner, okay. Also, we're gonna deal with the left Chirality spinner case. This generalizes to the other spinners, which is that being just the one other spinner, the right Chirality spinner. Yes, the right called Weyl spinner. So the dot product of this in itself is going to be chi A chi B GAB. So again, GAB is just going to play the role. This is going to be the spinner metric tensor component. Here's the Minkowski metric tensor component. This is for 4 vectors, and this is going to play the role of keeping our dot product invariant, which is something that we really like in physics, keeping things invariant except for components. But what's really nice, again, the components for this tensor won't change. I keep repeating myself too much. Sorry about that. So, okay, what do we do next? So let's show how the left Chirality Weyl spinner, the dot product is invariant. Let's actually show that. All right. So first of all, if it's invariant, it means that basically it means that XA, XB, GAB should equal XA tilde, XB tilde, GAB tilde, but GAB tilde is just equal to GAB, right? So and that equals X dotted with X. So if it's invariant, these should be the same, but this is just a generally shifted coordinate system. I believe that we're going to work with a boost. Oh, sorry, my glasses just fell off right now. Sorry about that. Oops. Just get them right now. Okay. So yeah, we are going to work with a boost, I think. Let me look at my reference. Is that a boost? Yes, we're going to work with a boost along the z-axis for our left Chirality spinner. We're going to new page. So boost along z-axis for this left Chirality spinner. So let's transform that. So okay, so yeah, let's begin. So again, XA, XB, GAB. Let's just calculate what this is going to be. Again, remember from earlier, it's going to be chi1, chi2 times e to the phi over 2, 0, 0. Oh, I forgot to mention what phi was. I'm going to talk about what phi is after this. And then, so what is our, you might be wondering, well, what is our spinner metric tensor? Did I even go over that? Yeah, I didn't even say what the spinner metric tensor was. Well, the spinner metric tensor, G, is actually going to be defined for now as 0, 1, minus 1, 0. This is our spinner metric tensor. It's the one that we have to choose in order for the dot product to be invariant. That's why we choose it. We can also derive it, but so this is going to be, so you just multiply it by the tensor, and then we multiply it by the same thing again. This should be transposed actually. So you have phi over 2, 0, 0. Again, we're multiplying by the same spinner component twice. Well, spinner vector twice, right? So this is why this appears. Wait. Yeah, that's why this appears twice. So 0, 0 e to the minus phi over 2, and then multiplied by x1, x2. So it appears twice, right? So it's going to be transformed twice by this matrix. And this is going to give us, again, x1 tilde, x2 tilde dotted with x1 tilde, x2 tilde, by the way. now this transpose, it's going to be the same thing, right? Since these are zeros. So phi over 2, 0, 0, e to minus phi over 2, 0, 1, minus 1, 0, e phi over 2, 0, 0, e to minus phi over 2, chi 1, chi 2. Alrighty. And now what do we do? Well, now what we do is we get to kind of multiply this by this guy over here to get chi 1, chi 2, e to the phi over 2, 0, 0, e to minus phi over 2. Don't want this video to go on too long. I'm going to rush a tad bit here. This is going to be 0, e to minus phi over 2, e to minus phi over 2, 0. Let's multiply this by this over here. Right, checking my reference. That is correct because yeah. Okay, so now what do we do? Well, now yeah, we have to multiply this by chi 1, chi 2. And now you have to multiply these two together. Chi 1, chi 2. We multiply these guys together. And we get 0, 1, minus 1, 0. I'm just speeding through this because I'm just checking my reference right now. I'm just copy pasting it. We could do this at least explicit matrix calculations, but just it's really straightforward. Just multiply these matrices together, and you'd get this. And notice that this is actually just the spinor metric tensor from earlier, right? And then these are our OG spinor components. Therefore, this equals XAXBGAB, right? These things. So this equals this, implying that the spinor is invariant or Lorentz transformations. Oh, well, under a boost along the z-axis. That's what I mean, to be specific. And yeah, we have covered everything that we wanted to cover today. We talked about the spinor field, how it assigns a spinor to each point in space-time. Talk about the Weyl spinors and direct bispinors, and Weyl spinors are the direct bispinor. We talked about chirality, which is kind of talk about the isospin of particles. The isospin allows the particles to enter weak interactions. No spin allows the particles to not enter weak interactions. The Weyl spinor. Talk about Weyl spinors rotation and boost. We talk about how the Weyl spinors transform rotations and boosts. Now they differ from the Lorentz transformation for the four vectors. And talk about Weyl spin metric, which allows the dot product between Weyl spinors to be invariant. Speaking of facts, I don't want this video to be too long. So yeah, that's it for Weyl spinors. Next video on spinors, we will talk about the direct bispinor and how it transforms. You can actually, I guess that's your homework. Try to figure out how it transforms. All you really do is just stick the Weyl spinors, transform those Weyl spinors, and kind of build a 4x4 component, 4x4 matrix for the direct bispinor. So yeah, that's all for spinors today, and have an amazing day. Please subscribe and like this video, all the cliche stuff. So yeah, bye.